Alrighty, today we are going to take a look at liquids and their different properties and compare and contrast them with what we already know about gases and what we will see with our solids. All right, so liquids are kind of in between. They have a definite volume, so we can't compress or expand them, um, but they have this indefinite shape, so they are fluid and they can be poured. Okay, so if we can pour them, they're going to flow. We can do this with our gases, we can do this with our liquids. Okay, here we have different types of liquids and talk about their viscosity. And when I worked for Quaker Chemical, we actually looked at how viscous different things were. This one is your alcohol, this is your water, this right here would be something like a syrup. And then we start getting into our gels and almost semi-solid colloids and talking about how viscous they are. Okay, like we said, they are a relatively condensed state of matter with a much higher density, and we can't really press them into one thing and take up a greater space than they have. They are slightly, ever so slightly compressible, but we're going to assume that they are relatively incompressible. But the big thing that these liquids do is they diffuse, okay? They flow. And according to the kinetic molecular theory, okay, they are in constant motion. So what I like to do in class is get some clear water, put it on a little light box, and one of the waters heat up, one of the waters be really cool, and this is a nice little demo that shows that, and basically drop food coloring into them. And you can see all these really cool little colors that flow back and forth. It's how they make the pensive in the special effect of the pensive is basically ink and water in all the Harry Potter movies. But what you'll see is the hot ones are going to diffuse much faster than the cold ones, and you'll see that the red spreads out much faster than the blue does. But eventually, even though we don't stir it, they are in constant motion, and we definitely see that they all mix. So if I added blue and green, it would end up making this really nice teal color. I usually add like a red and a blue, and it makes purple, etc. And anybody that has a cat knows that cats are definitely liquids. They take the shape of their containers, they fit in everything. All right, so when it comes to liquids, one of the most important things that we talk about is the vaporization of liquids. And that is a term, a general term that is used when we convert liquids to gases. And this is what happens below its boiling point. And we'll get to boiling point very, very soon. Okay, so vaporization is that escape of the molecules at the surface. You don't see bubbling like you do with boiling because it's not going to happen throughout. Okay, so this happens in opened or closed containers, and we do a lot of thought experiments in class with our bottles of water and what would happen if I took the lid off and I came back to the bottle of water in a month. Well, it would probably vaporize, or we like to call it evaporate. But if I kept the lid on and I came back into it in a month, it would still vaporize, but the lid would trap it on the top, and it definitely wouldn't change levels. Okay, so this one would decrease, but this one would increase. I also share pictures and videos of Frying Pan Lake in New Zealand, one of the coolest places I've ever been to because it's so hot. But basically, it's this big crater. There's all this volcanic activity underneath it, and the whole lake is literally frying. It looks like a big old frying pan. Oops. So, sorry about that. Accidentally exited out of there. But the next photo is a picture of me there in July when I went on a class trip. And yeah, it was really cold because it's in the southern hemisphere in July and it's winter. But this really, really warm water, almost boiling. So it's like 190 Fahrenheit, like 90 some Celsius. You couldn't touch it because it would literally boil your fingers off. But really, really cool to see. I highly suggest New Zealand. It's one of my top 5 places that I've been to. So, what is the difference between vaporization and evaporation? Okay, evaporation usually happens, and that is a term for open containers. Okay, so this would be like your puddles, this would be like a glass of water, a lake, a pool, etc. And vaporization is the general term that happens even in closed containers because we still see some of these particles moving. Okay, the particles are always moving. So when we talk about vaporization in closed containers, there is that buildup of vapor pressure. Vapor pressure is basically that sealed little bit of pressure of air, of gas. In soda, it would be CO2 that is above it. And when you open this up, that's the tss that you hear. Okay, it's that release of pressure. Some of the particles, when this builds up, is going to be forced to dissolve back into the soda. So that's why it looks like a bottle of water or a bottle of soda never ever change their volume because they are capped and they are closed. All right, but one important thing to remember is that this is constantly happening. Things are always moving, okay? Things, matter, gases, liquids, they are always moving. All right, but they eventually get to this point at which the rate at which they vaporize and the rate at which they condense are the same. So if they're the same, they are at equilibrium. All right, and sometimes we show it with a double-headed arrow like that. Particles still vaporize and they still condense. It doesn't stop. But if it happens at same rate, it looks still water. But as I show inside the really big containers that I have of my bell jars with the water in it, as soon as you drop some food coloring into it, even though it looks still, you see it move. So just because we can't see it doesn't mean it's not there. That's one important thing that I like to remember about science. Okay, so now that we know what vaporizing and evaporating is, what is the difference then with boiling? And why is boiling points so different? Okay, so a boiling point is the temperature at which the vapor pressure is equal to the external pressure. So the vapor pressure of the liquid equals the external pressure of the atmosphere. When the pressures are the same, there is no longer anything pressing down on your liquids to hold them in the liquid phase. Okay, normally atmospheric pressure is much greater than vapor pressure, so it stays as a liquid. Only the highest energy ones are going to evaporate off up at the top, which is why this happens to you when you are sweating. Okay, that's why you feel cooler after you sweat, or if you get out of the shower and stand in front of a fan, you feel cool because all the high energy particles leave and the cold energy particles are going to remain. But when the atmospheric pressure is the same as the vapor pressure, because you're heating this up, well, there's nothing holding it in the liquid phase anymore. So it all starts to boil away. And that's where you see bubbles throughout in your boiling phase. Okay, so important key terms. That is going to be the normal boiling point. The normal boiling point is the boiling point at 1 atmosphere, so at sea level. If you're below sea level, you're going to have a lower boiling point. If you're higher than sea level, you're going to have a higher boiling point. Okay, because there's not as much or too much of the force actually going to come about. All right, so this is really important to be seen on this vapor pressure curve. Okay, so a vapor pressure curve tells you the boiling point of different liquids at different pressures and temperatures. And this, again, is why we need to know all those different pressure units from the first video. Okay, so the vapor pressure is in torr. Okay, the temperature down here is in degrees Celsius. Here we have diethyl ether, ethyl alcohol, we have water, and we have ethylene glycol, which is the same thing as antifreeze. Okay, so at 760 torr, which is 1 atmosphere, which is the pressure at sea level. Okay, these are the normal boiling points of these different liquids. It should be no surprise that water is out here at 100. Ethylene glycol, if we extrapolate this, is like almost 200 something over here. But as you look at this chart, as you decrease the pressure, look at what happens to the boiling point of the water. Okay, the boiling point of water starts to drop down to 90 or to 80 or to 60 degrees Celsius. Room temperature is 25. Can we boil water at room temperature? Yes. What has to happen to the pressure? The pressure has to be low, very, very low, almost at a vacuum. And this is where in class I bring the great big huge bell jar in and we do the little experiment. Okay, so high altitude places like the Mile High Stadium in Denver, Colorado, have a different pressure than here in Philadelphia, Y equals Y, okay, which is at sea level. Okay, they have less pressure 1 mile up above in altitude. So where is it going to take longer time-wise in order to cook something? It's going to take longer in Denver. Okay, you'll see on a lot of different ingredients and directions, different high altitude directions. This is for shake and bake, and it says bake your chicken for 40 minutes, turn the chicken and bake it for 20 minutes longer, and it gives you your altitude in feet. This is for Betty Crocker, your high altitude instructions. It says how to change your stuff, add in a little bit of extra flour, and this is what happens when you bake at a high altitude with a sea level recipe. It won't get hot enough. So we change the boiling points completely. All right, so this little video embedded in my notes, I would definitely take an opportunity to see that. You can boil water at 25 degrees Celsius at room temperature. And even though you see it in the video, it's always best in person, so I do it in class. And people are like, whoa, that was boiling. Can it cook anything? But no, it cannot cook your pasta, okay? It would be like trying to heat it up with regular old room temperature, so that's not going to work. All right, so everybody likes to touch and feel and see what happens when we are actually boiling cold water, right? But it's all about pressure. Okay, boiling is really important. As I showed you in the beginning of the year, distillation is used in order to change a mixture and separate them into their different parts. So you heat up your liquids here. Once you get to the characteristic boiling point, this temperature thermometer will tell you, and a condenser will condense it back into a liquid for you, and you can definitely tell what the different liquids are by looking at the different temperatures at which you distill them. Okay, so you can use this to separate a mixture of liquids. Okay, alcohol and water. You can use this to separate and purify and clean out your liquids because our boiling points are physical properties. Okay, the temperature remains constant regardless of how much energy you have, so you can always tell by looking if it's graphed where the boiling point is because it's going to be flat. And we'll get into our phase change and curves and stuff, and you can actually separate all the different boiling points out for all your different liquids. All right, So this is our liquids, and I hope you liked all the videos. Definitely click on the embedded videos in my notes and check them out for yourself.